Section 5.4, Discrete Random Variables. A random variable, or RV, is a numerical quantity whose value depends on chance. And a discrete random variable is a random variable whose possibilities form a discrete data set, usually from counting. So a random variable brings us an opportunity to put a variable on probability situations. And the big deal for that for us is if we can bring in that variable, we're going to be able to calculate mean and standard deviation, and that in turn will help us to start doing z-scores and start asking, are things unusual or not. Let's go ahead and look at an example to introduce the idea of a random variable. At the beginning of the spring 2012 semester, I surveyed 65 car-owning stat students and asked them how many times they had personally opened the hood of their cars during the previous semester. And the results are as follows. For a randomly selected student from this group, let X denote the number of times they had opened their hood. So X is going to be a random variable here because I'm going to randomly choose the student. So it might be sometimes I select a student and I get one of the ones who opened their hood 3 times, and then X would be 3. But on another occasion I might get one of the 30 students who opened their hood never, or 0 times, and then X would be equal to 0. So what are the possible values for the random variable X? Well, I'm going to choose from one of these students in this group, and they opened their hood as few as 0 times, as many as 7, and every integer in between did occur. So what are the possible values for the random variable? I'll make a set for that. It could be 0, 1, 2, 3, 4, 5, 6, or 7. Any of those are possibilities for the variable. Of course, it's possible that a student would open their hood 10 times, but I'm going to randomly choose from one of these and ask them how many times they opened their hood that semester, and none of them in this set did open their hood 10 times. So use random variable notation to represent the event that the student opened their hood 2 times. So since X is the number of times they opened the hood, we can just say let's look at the probability that X equals 2. And then that X represents the number of hood openings, so that gets translated as the probability that they opened their hood 2 times. Another option for that would be to just put P of 2. And this is fairly common to do if there's only one random variable in the problem. So then it's understood we must be referring to that value of X. If there's X is the number of times they opened the hood, and Y is the score they got on their last homework assignment, then I can't just ask P of 2 because I don't know if that represents hood opens or homework scores. But in this case there's only one variable, so it's okay to use that shorter version. And then as far as finding the probability that X equals 2 goes, this is actually just review of material that we did earlier in the chapter. So we'd say, what are we randomly selecting? We're randomly selecting one of these 65 students, so the denominator is 65. And then for the probability that X equals 2, we'd say how many of them opened their hood twice during that semester, and 2 hood opens happened for 15 of those students, so it would be 15 out of 65. And then I could go to a decimal on that, so I bring in the calculator. Looks like 0.2308. Alright, and then the next thing is they want us to obtain the probability distribution of X. So we're going to formally define that on the next page, but what we want with a probability distribution of X is a table where we list everything that X could be together with all the probabilities for those X's. And X can be 8 different things, so I'm going to make a nice long table here since I'm handwriting this. And on the top, I'm going to list some values of X, and on the second row, I'm going to list the probability that our variable X would take on some of these possibilities for X. And X could be 0, 1, 2, 3, 4, 5, 6, or 7. And we already know that the probability that X would be equal to 2 is 0.2308. So I could write that right here underneath the 2. And then the chart would be telling us the probability of X being equal to 2 is 0.2308. Just a real quick comment on the notation. This isn't something you have to be really picky about or worry about too much, but the capital X represents our actual variable, and the lowercase x is just a placeholder for specific values it could be. So if little x is 2, we would plug that right here, and this would read the probability that x equals 2 is 0.2308. Don't worry too much about if you do a capital or lowercase x, but you will see that sometimes. I just wanted you to at least hear once why they do the two different ways. So then for the rest of these, I just need to keep doing divisions. So let me go ahead and calculate a few of them based on the chart. So the probability of 0 hood opens would be 30 out of 65. For 1 hood open would be 6 out of 65. We already did the one for 2, so I'll move on to the probability of 3, which is 5 out of 65. And let's see if we can get one more in there. For 4 hood openings, that happened twice, so 2 out of 65. So I'm just doing the count divided by the total, just like we've done in previous situations. Now I'm going to write these down. So the first one was 0.4615. The probability for 1 hood opening was 6 out of 65, or 0.0923. This is the one we'd already done previously. 3 hood opens happened 5 times. So the probability of that is 0.0769. 4 hood opens happened twice, so that one is 0.0308. Notice it's a 7, but followed by a 6. And then we have a few more to calculate, so let me go ahead and do that real quick. So 5 hood opens happened 3 times, and that's the same as the probability of 6, so I don't need to calculate it again. And 7 hood openings only happened once. So then filling in those last few, the probability of 5 times opening the hood would be 0.0462. Same thing for the probability of 6. And the probability of 7 hood opens is 0.0154. And this next step isn't mandatory, but if you think about it, since all of these frequencies add up to 65, these are representing the relative frequency calculation for that, so these should also add up to 1. And so let me go ahead and do that total and see if it works out just as a check. And I get 1.0001, which isn't any cause for alarm. I did round all of these different probabilities, so the fact they didn't add up to exactly 1 is pretty normal just due to the rounding error. And I happened to notice when I did these two, I was rounding up a 1.5 to a 2. So when you round a 5 up or a 4 down, you get bigger rounding errors. And we did that 5 up twice right here, so I'm not surprised that we ended up a little bit over. Alright, and then finally on this one, they want us to construct a probability histogram, and we've never done a probability histogram before, but we've done a relative frequency histogram, and these probabilities are basically the same calculation as a relative frequency, so they should have the same type of histogram as a relative frequency histogram. So I'm going to draw in my axes along the far left and across the very bottom. And then we'd want to think about a scale, and I'll label this as well. So this is my variable x, and then these are the probabilities for those x's. And the highest probability we have anywhere is 4615. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. So if I take that 0.4615 divided over 10 squares, this would be a scale that would work, but it's messy, so I'll round up a little bit to 0.05. So I'm going to have a scale of 0.05, and I'll number every other one. So 5, 10, 15, 20, 25, 30, 35, 40, and 45, 50. And then this is going to be single value grouping. So I want each bar to go from half mark to half mark. So ideally I'd like each one of these to be 2 bars wide. I've got 8 different ones to do from 0 to 7. Let's see if we have enough squares for 2 bars wide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We have just enough for that. and I'll go ahead and put my 0 here, put a double slash mark to show the break in scale, and then we're going to do every other one so that each bar is 2 squares wide. And that's just going to fit. And then we just want to go ahead and draw in our histogram bars. So the first one is the tallest one. Remember, it goes from half mark to half mark, so I'm going to start 1 square to either side of the 0 and go all the way up to 4615, which would be just a little bit above that 0.45 line on my graph paper. And then 0.0923, so just a little bit below 10% for that next one. And then 2308. Oh 0769, 0308, 0.046, so just barely below the line for 0.05, and we have 2 of those in a row. And then the last one drops down to 0.0154, about a third of the way up. And then I'm just going to shade these real quick as well. I think shading is particularly important when you have a couple bars that are the same height, and we actually have that right here. We have several bars that are similar in height and 2 right next to each other that are exactly the same height, so the different shading helps to distinguish those two. So there's our probability histogram. So when you make a probability histogram, it's fairly natural to ask some things like, okay, so what's the most likely occurrence? If I randomly selected a student, how many times would they have opened their hood? And so the taller the bar, the higher the probability. So 0 is the most likely thing that would happen, and 2 hood openings is the second most likely, and then kind of scattered among the others. Another question that you could ask once you've done a histogram for something that's quantitative, which this is you could ask, what shape is this distribution? So once you pause the video for a second, think about that, maybe write a shape down over here. I would argue that this one's a little bit tricky on shape. When I do this in class, a lot of people will say write exponential because the tallest bar is on the left and the shortest bar is on the right. But if you're going to do that, then you have to think that if we filled this in, that the bar for 1 would have actually been higher up here, and that the reason it's small like this is just due to random variation. I think when you have a little blip here that's shorter and then taller, and it's a small difference, random variation is a good explanation. But when differences are big, I think it's better, instead of going with random variation, to think of an alternative explanation for why the bar for 1 is so much lower. And I'm just going to throw my theory out there to you. You might have a different one. I think that we actually have 2 populations blended together here. Some of these students are students that no matter what happens are never going to open the hood of their car themselves. They would have somebody else do it, maybe a relative or a mechanic or something. And then there's other people who would open their hood, and maybe they need to, maybe they don't, depending on how their car's doing and how inclined they are to mess around with the engine. And so here is this tall bar to me. This is a mixture of some people who would have opened their hood and just didn't need to, together with a bunch of people who are just never going to open their hood. Some of these people may have had car trouble. It's just they didn't personally open the hood when that happened. And so we have that spike, and then we have this other group over here where they're apparently willing, and that one seems to be kind of right skewed to me, with the peak somewhere around opening the hood twice as a necessity during this semester. All right. Okay, continuing on with section 5.4 on random variables. A probability distribution is a listing of the possible values of a discrete random variable together with their probabilities. And we made one of those on the previous page. We made that chart of the different values of x together with the probabilities for each of those x's. That's referred to as a probability distribution. And I noted that if we add all those probabilities up, we should get 1. And in fact, we did not on the last page. We got 1.0001, but that was just due to rounding error buildup. All right, let's go ahead and look at another example of a random variable. From past experience, a car salesperson knows that the number of cars she sells per week is a random variable y, with a probability distribution as shown below. And a week is selected at random. Use random variable notation to represent the event that the car person sells exactly 3 cars, at least 3 cars, fewer than 7 cars, at least 3 but fewer than 7 cars. So the first thing just to take a moment to mention is that they're using a different variable here, y instead of x, and there's no reason that that has to be done, and it doesn't mean that we have to do anything different. It's just to kind of illustrate that a variable doesn't have to be x, it could really be any letter. And we'll see in later sections that we do use some different letters, fairly common for our random variable. So how would we write this in notation? The probability that she sells exactly 3 cars, I would write as the probability that y equals 3, since y is the number of cars she sells. At least 3 cars, I'd still write the y and the 3, but at least 3 means 3 or more, and so I could use the inequality with the inclusive symbol there, greater than or equal, to illustrate that at least 3 cars notation. And then fewer than 7, I'd write the number of cars y and the number 7, and then the number of cars is supposed to be fewer than 7, so that'd be a strictly less than. 7 is not included on that one. And then at least 3 but fewer than 7. Sometimes people get a little mixed up here, maybe they even write 2 different things, but if you really think through, like, what are they saying? They're saying the number of cars she's selling is in between 3 and 7, including the 3, but not including the 7. And when you have that sort of situation, what you want is the number of cars she sells y to be in between the 3 and the 7. When you have, we're going to write a 3-part inequality here. When you have that, the symbols always need to, if you think of them as an arrow, point towards the smaller number. And at least 3 is inclusive, so I'll put an or equal on that. But fewer than 7 is not, so I'm going to leave the or equal off on that one. This may be a little confusing because up here we said at least 3 was y is greater than or equal to 3, and now here we're saying less than. But notice that in both cases the symbol is pointing towards the 3 as the smaller number. When you turn the symbols around, or the place of the 3 and the y around, the symbol switches with it. And then let's look at some of the probability questions, starting with the first one, the probability that y equals 3. There's a temptation here possibly to start doing some calculations, doing some fractions, getting your calculator out. But remember, the job of a probability distribution is to give the probabilities for each of the different values of y to you. And up here we're told that the probability that y would be equal to 3 is 0.180. So all we have to do is go up there and fill that in from the chart. When they say y is greater than or equal to 3, it's the same idea. That could be 3 cars that she's selling, or 4, or 5, or 6, or 7, or 8. And what we'd want to do there is add all of those together, and we can get those off of the chart up above, and that would be fine to do that. And by the way, I can only take an or and separate that into addition if I'm using the special addition rule, which can only be used if these things are mutually exclusive. So if we ask this person what was the total number of cars that you sold last week, and she told me 4 cars and she told you 6 cars, she can't be telling us both the truth. Those are mutually exclusive possibilities. So it does make sense to go ahead and separate that into addition. It also makes sense, because we're adding up so many of them, to use the complement rule instead, and say, instead of adding up 3 through 8, let me subtract the 0 and the 1 and the 2 probabilities away from 1, and I can get the answer that way. Either way would be fine and get you the correct answer, but anytime I'm going to add up more than half, I'm going to turn to using the complement rule instead and subtract out the fewer things. So looking at how that would turn out, that would be 1 minus, just going to the chart up above, the probability of 0 is 0.135, minus the probability of 1, which is 0.271, and that's also the probability of 2, is the same amount. And then I can go to the calculator and figure out what that is altogether. So I get 0.323. And I just want to point out that if I had chosen to add up from 3 to 7, that would have been the same answer, 0.180, 090, 0.036, 0.012 plus 0.003 plus 0.002. I still get the 323, but I'm adding 6 numbers. You can just look at it on the calculator. That's more calculation than doing the subtraction. So either one works, but if you're going to add more than half, I would suggest using the complement rule and subtracting away what you don't want. Alright, let me go ahead and separate this off since we invaded the space of the next one a little bit. So what's the probability that y would be less than 7? I would use the same philosophy here and say that what they're asking me for is 0 all the way up to 6. And I could add all those together, but it'd be a little faster to subtract away the ones I don't want. And if I want 0 through 6, then I don't want 7 or 8. And I can get those from the chart. The probability of 7 is 0.003, the probability of 8 is 0.002. If I add those up, that's 0.005, subtracting from 1, I would get 0.995. And I'm not going to show you the addition way, but you could check if you want. Go up there and add 0 through 6 as probabilities together and you'll get the same answer. But it's faster to subtract these two than to add all the others. And then finally, the probability that the number of cars she sells is somewhere between 3 and 7, including the 3 but not the 7. That would be the probability of 3 and 4 and 5 and 6, but not 7 because it's not included. And then I would just go to the chart and get those. So the probability of 3, 4, 5, and 6, those are the ones I want. So that's 180 plus 0.090, 036, and 012. Let me just go ahead and bring in the calculator. We'll add those up, and that will finish this off. So it looks like we get 0.318 for that answer. Alright, so that finishes up that example. The mean and standard deviation of discrete random variables. So one of the reasons that we do random variables is because the notation is kind of nice, as we saw in the couple pages that came before this. But the main reason we do it is so that we can get a mean and standard deviation for random events. So we're going to build a formula for the mean and standard deviation of random variables, and we're going to use our old group data formulas from chapter 3 to do that. So for the population mean for group data, we had the sum of the xf's over n. And the order of operations here would be to first multiply, then add, and then divide by n as the last step. But it turns out that you can distribute that division and move it inside like this, where the order of operations becomes take each frequency, divide by n, then multiply by x, and then add as the last step. So essentially that's the distributive property. Now the reason that we'd want to do that is because f over n for population data is population relative frequency, and we said earlier in this chapter that when you calculate a population relative frequency, that's the same as calculating a probability. And so that gives us a way to introduce probability and our random variable into a formula for the mean. So the mean of a random variable x is also called the expected value. And the symbol for it is mu with a subscript of x, and it's equal to the sum of each x times its probability. It's important to remember the order of operations here is to multiply first and add last. So each x gets multiplied by its probability, and then after we've done all the multiplications we add them up, and that will be the mean of our random variable. Alright, let's go ahead and see how this works with an example. So the random variable x is the number of goals scored by the losing team in an NHL game, which is National Hockey League, and its probability distribution is as follows, where the number of goals scored by the losing team can be 0, 1, 2, 3, or 4, and then the probabilities for them having that many goals when they lost a game is shown right below that. So we've got this chart here but no directions, so let's go down a little farther so we can see what they want us to do. Find and interpret the mean of the random variable. So to find the mean of the random variable, we want to do the sum of the x's times the probability, and as I just mentioned, the order of operation is that the multiplication comes first. So what we want to do in this chart is take the x's and p of x's they gave us and list them vertically, and then make a new column where we start doing these products right here of x times p of x. So 3 of them have been filled in. 0 times anything is 0. 1 times this probability gives us that probability back. And then we'd want to fill in these two by doing multiplication. So to fill in this spot right there, I'm going to want to do 2 times 0.3191. So let's see what that is. That gives us 0.6382, so I'll fill that in right here. And just make a note there, so that calculation is giving us that number right there. And then we'll go ahead and do the next one as well, so that would be 4 times 0.0213, and that is 0.0852. And at that point we've done the multiplication of every x times its p of x, so all that's left to do is the sigma, or the sum. So now I'm just going to add vertically 0 plus 0.4043, and so on. And when I add that up, I get 1.383, and that would be the mean of the random variable. So I guess we can do that right down here. Find and interpret the mean. The mean of x is the sum of the x p of x's, and the sum of those x p of x's was 1.383. And they want us to interpret that as well. Anything that's a probability type of number, we're going to interpret as a long-term type of event. So we're going to say after randomly selecting many NHL games. So this many bringing in the long-term idea. So after randomly selecting many NHL games, we would expect the mean goals by the losing teams in the game selected to be about 1.383. So a few things worth mentioning here. One of them is sometimes people get a little confused that I say we found the mean and yet we just did multiplication and addition and no division. So I often ask people, how can you do a mean without dividing? And the answer is you really can't, but the division normally would have happened at the end, but the way we're doing this formula, it happens inside the probability. So whoever calculated these probabilities did the division for us ahead of time, and so we're just left doing the multiplication and addition. The other complaint that we'll get sometimes from people is, how can you say the expected number of goals is 1.383 when it's impossible that a team would score 1.383 goals? It has to be 0, 1, 2, 3, or 4. And we're not saying we expect any team to that lost a game to have this many goals. We said if you took many games, we'd expect the mean amount of goals. So sometimes it'll be 0, 1, 2, 3, 4, but if you do a lot of games and you average the different results you get, you expect something around 1.383. Alright, so the interpretation of the mean of a random variable is the expected mean value after a large number of trials. And then similar to doing the mean, we could also do the standard deviation of a random variable. And I'm not writing out the transition this time, but if you were to look back at the grouped data formulas for the population standard deviation, you'd see something that looks roughly like this, but instead of the p of x, you'd have an f over n. And so we're just doing that same move of replacing the f over n by probability. So they want us to obtain the standard deviation of the random variable, so I want to use this formula to do that. Anytime I have a formula with a sigma in it, I would like to go back to my table and then make a column that has whatever is after the sigma, so in this case x minus mu squared p of x. And we already have that column here, x minus mu squared p of x. And so I just need to now go ahead and fill in the couple that are missing and then find the sum or sigma of that. So let's think about this one right here and what that one would be. So we're supposed to start off with parentheses and then the x for this row, which is 2, minus the mu of x, which was this 1.383 value. We're then supposed to square that and multiply by the probability for this row, and the probability for this row is 0.3191. So let me go ahead and bring in the calculator and do that calculation. So open the parentheses and then 2 minus 1.383, close the parenthesis and square, and then times the probability 3191. So in this spot we get 0.12, and thinking about decimal places, since the others have 5, we'll do 5 here also, so that'd be a 148. And just to kind of check our work on that one, let's take one of the ones that was filled in already and try that. I'm going to hit second enter to pull up this old calculation. On this row the x is a 3, the mean is the same on every row, and the probability for the row with 3 is 0.851. So if I'm doing this right, I should get this 22251 number, and there it is. So now let's do the one that's missing at the bottom, where the x is a 4, so I'll enter that in, and the mean stays the same, but the probability is 0.213, so I'm replacing the probability of x with this number, and now I have 0.1458, and then it's a 7 but followed by a 7, so that'd be another 8. And then what I really want when we look at the formula is the sum of all that. So bring the calculator back in and add all of that stuff up. And the sum there is 0.87472. And unlike the last time with the average where the sum was our answer, this is not the answer for the standard deviation. It gets us really close. We just need to take the square root of that still. So the standard deviation of this random variable would be the square root of 0.87472. So that will be our last step on getting this standard deviation. So the square root of 0.87472. And then standard deviations are always written with 5 digits or significant figures, so 935 and then 26. So that would be the standard deviation of the x values. Alright, so we just found the mean and standard deviation using the formulas and going through the table, and there's nothing wrong with doing it that way except that it can be kind of tedious. So I want to show you real quick how you could do this on the calculator as well, and the idea would be to take the x values and put them in L1, the probabilities in L2, and then to start creating these other columns using L3 and L4. So L3 would be x times p of x, which would be list 1 times list 2. And then we'll have to get I'll show you how to get the mean, but once you get the mean, this column right here could be L4, and we'd want that to be open parentheses, the x values, which are in L1, minus the mean, which we will have found at that point to be 1.383, end parentheses, squared, and then times the probabilities, which we put in L2. So if we do this in the calculator, then we can get all of these numbers at once, and we can also then use the list menus to get the sum. So let me go ahead and just show you that process for this data set real quick. Slide that over. So I'm going to hit the stat menu and go into edit, and I'm going to enter the x values into list 1. And list 2, I'll put the probabilities. And if I want to double check that real quick on the probabilities, I could go into list, math, sum, and find the sum of L2. I'm doing that in just a normal square or cell of L3 as scratch area, and I get 1, which is what it says it was supposed to be. So now I'm going to clear L3, and I'm going to let it be L1 times L2. And you'll notice that these numbers match the different ones that we have written down in our table from our calculations. So the mean would be the sum of L3, so I would go into the list menu and math and sum of L3, and I get 1.383, which is the same as what we got before. And then finally, to do the standard deviation, I could clear L4 and let it be as it says over here, open parenthesis, L1 minus 1.383, close parenthesis and square, and then times the probabilities, which are in list 2. And if I do that, I get this column. And then finally I could go over to one more square for scratch area and do list math sum and do the sum of list 4, and that would give me the number that's used inside of the standard deviation. And so that's the 87472. Now you might notice here it's a 1. That's because we rounded these, so there's a little bit difference in the rounding. I wouldn't worry about that. You could do it either way, and I would accept either answer. Now that would be making the whole table still, but using the calculator, the best option of all doesn't even require the L3 and the L4, so let me go ahead and clear those out. If you just get your x's in L1 and your p of x's in L2, you can actually kind of, in a way, cheat a little bit on the calculator here and go stat, calc, one variable statistics, L1, comma, L2. And I say cheat a little bit because this is the grouped mean and standard deviation formula on the calculator, and it's expecting L2 to be frequencies instead of probabilities. But it turns out, since we built our formulas off the group data formulas, that if we use this, we'll still get the right answers without having to do the list 3 and the list 4 ourselves. So you can see here that for the mean, it's saying 1.383. It's calling it x bars, so we would have to realize that's mu of x. And then the sigma of the x is 0.93526, which is the same thing we got by doing all that other work on the table. The n equals 1 doesn't really make sense, but that's because it's thinking that the frequencies were those decimal probabilities, so when it adds up the total frequency, it's actually getting total probability. Alright, so you can use any of those methods. You can make the table the long way by hand, you can have the calculator do the table for you, or I don't mind if you just go straight to using one variable stats L1, L2, so I'll just put a note on there too, so we can hit stat, calc, and then choose one variable statistics, and then just tell it where our data is L1, L2, and then press enter. And that's a shortcut that would allow us to actually not bother with those columns. Those columns still happen, but they're happening inside the calculator. Alright, now let's go ahead and finish this off by looking at some uses of the mean and standard deviation. So one of those would be to ask a question like this: would it be considered unusual if the losing team in a randomly selected game had scored 4 goals? So if you know hockey, you'd know that'd be a bit of a surprise to score 4 and to lose. But what if you don't know hockey? It's okay, as long as you know the mean and standard deviation, that'll allow you to do a z-score. So they want to know if 4 goals would be unusual, so I'm going to use that as my x, minus the mean, which is 1.383, divided by the standard deviation, which is this number here, the 0.93526. And then once we get a z-score, just from a statistical point of view, without any hockey knowledge, we could still say whether that was an unusual event or not. So let's see, 4 minus 1.383 divided by 0.93526. So I get a z-score there of 2.798. And we know from chapter 3 that anytime you get a z-score that is over 2, you've just seen an unusual event. So would it be considered unusual for the losing team to score 4 goals? I would say yes, because 4 goals is more than 2 standard deviations away from the mean. Alright, continuing on with that previous example, they want us to find the expected range for the random variable. And so to do that, I would want to take the mean and add and subtract 2 standard deviations of that mean to get the boundaries for things that are 2 standard deviations away. And so just bringing in our work from the previous page, the mean was 1.383. and the standard deviation was that 9.3 number, so plus or minus 2 times 0.93526. And I'll do that with a minus and a plus to get the two boundary numbers. So 1.383 minus 2 times 0.93526 gives negative 0.48752, and if I do that with a plus sign, I get 3.25352. Now, if the variable we were working with was continuous, I would say the expected range is anywhere between negative 0.48752 and 3.25352 goals. But when you have a discrete variable, you want to think about what are the possibilities for your variable. Kind of imagine those on the number line. We have 0, 1, 2, 3, and 4, and I'll just put dots for those because it's discrete. And then I'm going to draw like fences where these numbers are, so the negative 0.48 is maybe right here, and the 3.25 is right here, and then anything in between those is expected. So what's in our expected range? Any number of goals from 0 to 3, but not including the 4. So I would expect the losing team in an NHL game to have scored somewhere from 0 to 3 goals. And this, by the way, is another way to see that 4 goals is unusual, which was the question in Part C, because it's outside of our expected range. Alright, let me draw a line here just because we're blended in with the piece below. So the interpretation for the standard deviation of x, a random variable, is it measures the standard deviation of the x values obtained after a large number of trials. Which is to say, if you observed many NHL games and recorded the score for the losing team after a bunch of those and then found the mean and standard deviation, it should be close to this 0.93526. And then we can also use it together with z-score or z-scores and the empirical rule. To assess whether or not a given value of the variable is unusual or not. Remember, the empirical rule is where we got the idea that anything more than 2 standard deviations away from the mean would be unusual. And then the calculator note, which I showed you on the previous page, is you can compute your mean and standard deviation of a random variable on the TI by entering the x values into L1, the probabilities into L2, and then just go stat calc one variable statistics L1, L2, and you can just do that instead of having to do the whole table. Alright, that finishes up section 5.4.